Good afternoon, ladies and gentlemen, and thank you so much for joining us today. On behalf of AUVSI, I am very pleased to welcome you to our first webinar of 2021 on using initial and position measurements in testing and survey projects, bridging the gap between autonomous vehicle development and survey. My name is Shannon Whitney Walker, and I am the Education Manager here at AUVSI and your host for today's webinar. Before we get started with what you're here for, I have a couple housekeeping items to note. All of the participant lines will remain muted throughout the broadcast. A recording of the program is underway and will be emailed to all attendees and posted to auvsi.org within the next few days. If you're listening today and you need assistance, please just send a note to our AUVSI support team member using the chat box on the right side of your screen. If you do not see the chat box, simply click the chat bubble icon that is located at the very bottom right-hand side of the screen, and that should open the chat box panel. After the presentations today, we will open up the session for Q&A. Attendees, you are welcome to and encouraged to submit your questions at any time throughout this webinar using the Q&A box on the right side of your screen. The questions will be saved and answered at the end of the presentation. Please note, the Q&A box is different from the chat, so please make sure to submit all of those content questions for our speakers using the Q&A box. It can be found directly underneath the chat panel. So let's get started. We would very much like to thank our sponsors for today's webinar, Navtech GPS and OXTS. We are very excited to have two excellent speakers from those companies with us today. Paris Austin, the Business Manager of Survey and Mapping at OXTS, and Frank Boynton, VP and CTO at Navtech GPS. So our first presenter will be Paris Austin. Paris has been with OXTS for a number of years, holding several senior roles, previously managing application engineering at OXTS, but most recently heading up the survey and mapping department. Paris has been instrumental in the development and delivery of key products within OXTS, liaising closely with customers and partners alike to deliver cutting-edge inertial navigation technology to multiple industries. And we'll also hear from Frank Boynton, the CTO and Vice President of Navtech GPS. Frank's primary focus has been on precision GNSS systems and solutions requiring high accuracy GPS real-time centimeter level applications. He has personally been involved with integrating GNSS solutions into many of the top unmanned UAVs and UGVs used by the US military. Frank also consults and designs systems for GPS and GNSS integration into LiDAR systems, as well as photogrammetry, tracking systems, relative position systems, positioning systems, and many other applications involving precise positioning. So thank you both so much for being here with us today. And with that, I will hand it over to you, Paris.
Thank you very much, Shannon. And we're really happy to be here today, joined by myself and Frank. We're going to cover quite a lot today, so I'll let Frank do the introduction and then we'll get straight into the technical content. So I'll leave this with you, Frank.
Hello, I'd like to thank everybody for attending and for hosting. I'm just going to do a quick intro and then I'm basically going to turn it back over to Paris, who is going to go ahead and tell you everything else that you would like to know today. We're teaming up with OXTS for this webinar today. OXTS is the manufacturer and support center for all things INS, and we are the North American distributor for OXTS. The things that you're going to learn about today are inertial navigation and what are the benefits. Paris is going to go deeply into that, and just always keeping in mind also that he will be talking about specific applications in many cases. However, those same applications and uses can be used across a wide band of platforms for a lot of different things. We'll also be talking about uses for development of autonomous vehicles. OXTS has been in the vehicle market since day one. Since they started, they have been doing autonomous vehicles as well as manned vehicle and vehicle testing, which they excel at. We'll talk about the validation of autonomous vehicles using INS inside the vehicles and using it as a truth model as well. We'll also talk about how inertial navigation bridges the gap between autonomous vehicle and survey industries. We'll go into mobile mapping and many other applications to explain this. We'll also go into the importance of georeferencing your data for survey applications. Now I'll turn it over.
Okay.
Before I do that, I think I've explained a little bit of this already. We are the North American distributor for OXTS. If you have any questions afterward for sales, you can contact either ourselves or OXTS directly. Paris?
Thank you very much, Frank. So moving on straight away to OXTS's core technology. As Frank said, we build, design, and manufacture inertial navigation systems across a wider range of applications. Predominantly, OXTS is operated in the automotive market, as Frank referenced, developing vehicle dynamics applications, but more and more the advanced driver assistance systems and fully autonomous vehicles in the recent years. The way that we do that is the combination of inertial measurement unit and GNSS. The combination of the two, which is I'll touch on much more detail in a couple of slides, but instead of switching between them, we effectively use the strengths of both, and we end up with a solution that is much better than the sum of the parts of each individual component. The biggest benefit of GNSS is the absolute position reference it gives you with respect to the Earth, and that we found is really important both on the automotive and survey side, not just in terms of having that latitude, longitude, and altitude measurement, but also having reference points that if you collect a data set and a third party collects a data set, you can synchronize them across the same coordinate frame and not have to do a whole bunch of post-processing work or rejigging of that data in order for your systems to work well with theirs. So touching just on what is inertial navigation, and then we'll go into the specifics of how we use it. An inertial navigation system is that combination of an IMU, inertial measurement unit, and the GNSS, the Global Navigation Satellite System. The benefit of both of them effectively is that an inertial measurement unit calculates and measures its own intrinsic motion, so that's acceleration in a linear and angular rate sense, and then also pairing that with the GNSS, which gives you a position and a velocity update, as well as raw satellite range data. The two drawbacks of both: an inertial measurement unit will randomly drift over time, whereas a GNSS update is absolutely accurate every time you receive one. So the drift methods of both is completely mutually exclusive. And the benefit of that is when you have good GNSS signal, your IMU is being scaled to match that of the GNSS output. And when you have no GNSS signal, the IMU continues to output at its full data rate, and you get the benefit of both systems while getting the negatives of neither. The result then is nanosecond accurate time thanks to the GNSS constellations and their atomic clocks. You get 3D global position and you get 3-axis orientation, so heading, pitch and roll, or yaw, pitch and roll, depending on your use case. The third benefit in terms of data output is you get a real array of accuracy outputs, diagnostic and status updates, so that you can actually track in real time how well your system is working, how well the navigation system of the INS is working. And so you can make more intelligent decisions around whether the vehicle should speed up, slow down, because conditions are good or bad, and also then whether the data that's coming out of the vehicle is valid or trustable or not. So one of the questions we do get quite a lot is the question about why should I use an INS versus just using a GNSS receiver on its own? And there are three kind of key points to that. The first one is that GNSS, you may be able to achieve heading, pitch and roll updates using GNSS and using a combination of dual or triple antenna setups. but this is dependent on you having good GNSS conditions in order for you to get those outputs. In a single antenna GNSS receiver, you will get position and velocity, but you would not get heading unless you were moving. It's as a result of the velocity vector coming from the system. And so if you were static, a dual antenna GNSS receiver would still be able to give you heading, but you would get no pitch or roll from that. The IMU then gives you that heading, pitch and roll at a very high data rate and a very low noise output. And so the benefit of an INS outweighs that of a GNSS only system. That really applies to things like UAV applications, where this second point maybe doesn't come into effect. And that second point is an INS with that IMU included gives you continuous output regardless of what the GNSS conditions are. And so, say for example, you went under a tunnel, in a tunnel and out the other side, or under a bridge, then a GNSS only system would give its last update just as you enter the tunnel, and your first update after that would come as you emerge from the tunnel. An INS, though, would be able to give you continuous outputs during that outage, especially with things like bridges, where it's a brief few seconds of outage. The INS can really absorb that completely with negligible drift, but can still give you that 100 or 250 hertz output, whereas a GNSS update rate, even in good conditions, is normally a lot lower than that as well. When you're talking about autonomous vehicle navigation, high update rate and reaction time to stimulus is really critical to being safe and fully operational all of the time. Third point around why INSs are more valuable than GNSS on their own is that an INS is Kalman filter, which combines the GNSS data with the IMU intelligently and runs an error feedback loop that rejects any unexpected updates, can give you more than a standalone system of GNSS plus IMU that are effectively tacked together into one system, but not actually tightly integrated. Things like gravity are a really key, valuable asset to an IMU, because you can sense where gravity is on your 3-axis accelerometers, and therefore you can get roll and pitch purely from where you are sensing gravity. So just a brief comment on what tight coupling is. OXTS INSs offer tight coupling, and that is that the concept of combining the raw data from each sensor, the GNSS and the IMU, and combining it at the point of calculation of position and orientation, rather than taking position from the GNSS receiver and then adding heading, pitch and roll to the output solution, thanks to the IMU's output. So when we do combine the two systems in the tightly coupled solution, we take the satellite pseudo range and carrier phase data, and we merge that with the angular rates and the accelerations of the IMU. And what that gives us is a very robust inertial navigation system, which can reject data from the GNSS, which is unexpected. For example, a 10-meter jump to the left as you're traveling along a straight road, because of multipath signal on the GNSS, that would be intelligently rejected as a result of the IMU's accelerometers not seeing a lateral acceleration to the left. So that's why tight coupling is advantageous, and it's a solution that is offered in all OXTS's INS. So moving on to the benefits of inertial navigation for the development of autonomous vehicles, we'll touch on the development and the validation of, because OXTS's systems are used in both applications. But the first step of development of an autonomous vehicle would be to calculate the mobile vehicle, the autonomous element that you are testing and developing for sale, and effectively calculate where it is with respect to any obstruction. So that could be a lane, that could be the curb, it could be a parked car, it could be a geofenced area that a UAV is operating in, or buildings, or any number of obstructions that vehicles come across in their daily operation. So the first stage is to know where am I, and that comes from the INS's intrinsic measurements that it calculates, and that is the GNSS's latitude and longitude and altitude, and then its heading, pitch and roll. From that point, you can have a surveyed map of the area that you're working in, and you can say, okay, I know where my lane markings are, I know where the parked car is in this scenario, and I know where all the buildings are. With global coordinates, and you can say at any instantaneous moment in time, where was my autonomous vehicle when it effectively should have been making a decision to either avoid a parked car or stay a certain distance from the lane. And you can validate whether or not that did occur by having that map file combined with the real-time output of the INS. And specifically at OXTS, we have software that does that relative calculation, and we call it RT range. And you can do vehicle to infrastructure measurements like this, and you can also do vehicle to vehicle updates. But really, the first stage of development would be to validate that your autonomous vehicle can avoid colliding with or safely pass by any of these obstructions that it comes across. And if you've seen any of the videos of any autonomous vehicle or robot being developed, they will introduce more and more obstructions over time and start to build up the complexity through which the autonomous vehicle can effectively adapt to the environment and continue its path that it's trying to go on. So the INS tells you that 3D space and orientation, but the high data rate and low latency also allows you to use the navigation data from the INS as a path following data input. So because you have that high data rate, you can make corrections to your path following trajectory. You can run that error feedback loop to say, I am X centimeters away from where I want to be. And so a correction of 3 centimeters laterally will put me back on my path. The INS can provide you with that data to allow you to make the intelligent decision as to what your next step is. And all the while, I should say that this is being done to centimeter level accuracy, thanks to Rtk Corrections, and then a very high accuracy of heading, pitch and roll as well. So a few examples of the vehicle to infrastructure scenarios that might be being used by any one of you today or in the future. The one OXTS is most familiar with is the autonomous car development. So whether that is with respect to other vehicles parking in parallel parks or bay parking, it will need to not just know where the lane markings are, but also how far away it is from the other vehicles as it's approaching the parking space, but also any number of other cars around it that are in the parking lot at the time. So what you can do there is survey your lanes and your parking bay limits, and then you can at any one time get the perimeter of the car measurement and measure how close is my vehicle to the edge of a parking bay line. And therefore you can validate whether the ultrasonic sensors on the autonomous vehicle are doing what they are meant to be doing. And whether if you've got camera systems as well identifying the lane markings, you can tell whether you're within the space. Similarly, ultrasonic or LiDAR sensors will be telling you that very near field obstruction avoidance data that can tell you, am I too close to the car on the left and the right, or am I dead center of the two? Taking each one in isolation, though, can often lead to error in the output. Say, for example, you don't take into account the lane markings, you just try and put yourself in between the two already parked vehicles. Could lead to you parking your autonomous vehicle over the line on one side, so that when one of the other vehicles leaves, you're left with multiple vehicles parked in the wrong place. Another example is taking an autonomous train, whether that is measuring its distance to traffic signals or stations that it is approaching. You may find that you want to validate the development of when the vehicle brakes in order to safely come to a stop in the station. The INS can tell you that acceleration force. It can also tell you the time at which deceleration started to take place, and you can constantly monitor the distance between the two. And you can measure a variable which we call time to collision. So as you approach the station, you would expect time to collision to come down at a safe value. And if there is a collision that is expected, it will tell you then in real time as to whether the train needs to decelerate faster or if it's on course. Probably the most popular and third example of vehicle to infrastructure development at the moment will be UAVs. As UAVs become more and more common in terms of commercial and industrial applications, there will be the need to validate whether the autonomously piloted UAV is actually following the right path and also taking off and landing from the right location. So similar to an autonomous car, there will be a number of obstructions that the UAV needs to avoid, whether that's being operated in an airport or other closed circuit kind of environment, where there are a lot of moving parts and a lot of infrastructure wherein it needs to operate safely. You can have an INS on your UAV. You can have the static latitude, longitude, altitude location of your landing pad, and you can calculate whether or not the UAV is coming down to land on the correct spot or whether it's off laterally or longitudinally. So there's, as Frank said at the start, there are a number of applications that this is relevant to. These are 3 examples, but it by no means stops at this point. It might be that we've shown a car, a train, and a UAV, but any vehicle that needs to know its 3D position and orientation will be benefiting from inertial navigation in these environments. The next stage of an autonomous vehicle development piece then would be that addition of other moving vehicles into your test environment. So, for example, this previously may have been a parked car. It may have been even not a real car, a soft target, so that you can actually risk crashing into it without major cost. And placing an INS in your vehicle under test and target vehicles, you can have any number of target vehicles also collecting data in real time. You can then calculate the relative range and orientation between your test vehicle and any target. So what that would allow you to do is very rapidly create that feedback loop around, we've created an algorithm based on integrating a number of onboard sensors to our autonomous vehicle, say it is LiDAR or stereo camera or radar, or any number of these sensors that are being used to sense both vision and motion. And you could then say, where was I when I passed this manually driven vehicle? So autonomous vehicles having to operate alongside human operated vehicles is a really key safety point. You might say, was it safe? Was it beyond safe? Was it being overly cautious? And can we increase the speed, or do we decrease the speed because it actually isn't operating correctly at the higher speeds? You can get all of that data as a result of having an INS in both vehicles. The other point to add is that with an INS in both vehicles, you may actually have a building in between your 2 vehicles at any point, and it may be that your test is, how well does my autonomous vehicle do at detecting when another moving vehicle comes out from behind a building or from behind an occluded field of view, and therefore you will know how good the reaction times of the autonomous vehicle are and whether there is any risk to the potentially passengers of the other vehicle. So because of that non-line of sight requirement between the 2 systems in order to know where they are relative to each other, you can then also include the vehicle to infrastructure measurements. You could have a building modeled in your map file that you're using, and you can actually calculate visibility, your expected visibility of the target vehicle. And then that allows you to effectively say, I couldn't see the target vehicle, but that's okay because I shouldn't have been able to see it because the building was still in the way at that time. Or if it did start braking unnecessarily without seeing the target vehicle, you know that that is something that you go back around the feedback loop and adapt the algorithm of the autonomous vehicle to be less sensitive to what it is detecting. So there are the 2 main elements of autonomous vehicle development in terms of the ways that inertial navigation can be used to develop them. There is also the element that an INS of varying performance level can be used as a component within the system rather than as a verification device. So all of these data points that you would be receiving, as well as speed and acceleration, are all valid measurements that can be helpful in terms of localizing the vehicle in 3D space. And then that would allow you to say, my LiDAR or camera system is not detecting any obstructions around where I am, but my INS is giving me my global position, and I know that within the map that I'm operating within, I know that there is a road sign up ahead that is a stop sign, and therefore the vehicle should be coming to a stop, even if it has not yet detected where that stop sign is. So a rather high level overview of how these things tie together then in terms of multiple autonomous vehicles working in the same space, but also operating in the same space as manually driven vehicles or potentially even pedestrians. One example is an open top mine. So GNSS is still very much available, but may be obstructed in an open top mine. UAVs will have no problem in terms of GNSS tracking, but they will need their heading, pitch, and roll updates to come from an INS in order to geo-reference LiDAR or camera data that is being taken on board. So an autonomous vehicle, UAV specifically, just to cover the stuff in purple in the top right, it would not just need to be able to autonomously navigate around the closed area. It would need to know where it's taking off from, where it should be landing, what obstructions it should be avoiding in the area. That can all be done by tracking its own accuracy to centimeter level, own position to centimeter level. But then also the data that is being output by the INS can be used to actually collect valuable data, not just navigate the vehicle. So you can have your UAV flying the same flight path every day or multiple times a day, and then it can collect LiDAR data that will geo-reference a point cloud, and you can perform multiple different applications like volumetric survey of the resources left in the mine or asset management. So is any vehicle or obstruction in a position that it wasn't in the previous day, and does that raise a safety risk? One of the other key points then is autonomous vehicles may be operating almost like as a hive mind or platoon kind of situation, where they may be all following the same path, but they need to be aware of each other in order to not obviously collide with each other or pose any risk in terms of you don't want maybe two trucks in the same area at once because of safety risk. So an INS in every vehicle can mean that you know where each one is. You may have a control tower that monitors all of the data from every vehicle in the area, and you can actually say whether or not you've got a safety issue because one vehicle is still in the area when another vehicle is entering. So that that group collective behavior, it can also be helped by tracking each vehicle's position and orientation with an INS. And then similarly, manually driven vehicles in the same space, because obviously where we are today in terms of the technology will mean that only a selection of the vehicles in any given environment will be autonomous, and there will be a predominant nature of manually driven vehicles being in the area. It is obviously paramount that any human operator is safe at all times. So these autonomous vehicles need to be as aware of the manually driven vehicle as they are of each other. And so their near field detection needs to be really safe and really reliable. And you can use the INS in this vehicle as well to track whether or not it's at safe distance or if there is relative speed between the two vehicles that is going to lead to a collision. And then finally, there is that vehicle to infrastructure element where you might have a train on the rails that is delivering all the resources that have been delivered by the trucks to the train. It may autonomously then take the resources to the port to be shipped elsewhere. There are countless applications. This is just one environment in which many autonomous vehicles could be being used. In every single one, inertial navigation can add value to that and give you that reliability and repeatability that will allow you to trust the development of your autonomous vehicles as well as use them in everyday environments. So just one point then, obviously you would validate your development as you go, but when you believe you have a fully autonomous vehicle ready for commercial sale, it's really important that you can prove not just to your customers, but also to regulatory bodies that your vehicle is fit for purpose. And that can be done again by using an inertial navigation system, both in the vehicle under test and be it a target vehicle or a static object. So for example, if you're proving the repeatability of the autonomous vehicle's ability to land on its landing pad every time, you could have the INS on the UAV and you could have your static points surveyed in for where the landing pad is, and you could do your takeoff and landing procedure 100 times and validate how much variation was there on where the vehicle actually landed versus where it believed it had landed. And that's something the INS can give you in terms of data output and data reporting. It can tell you, similarly, with the example of a road vehicle and an autonomous emergency brake test, it can tell you not just did the AEB activate or not, or did it activate in time, but it can also tell you a number of other things. So it can tell you when the threat was detected based on when the vehicle started braking. It can tell you what the force of the acceleration was. It can tell you the time, which is really important. It's the nanosecond accurate time from GNSS is a real value add to the capability of the INS, but it can also tell you that relative distance. So it could tell you that the crash occurred, but if it didn't occur, was it still at a safe distance or was it at 10 centimeters? So you're really cutting it fine, and that is a too small tolerance of error for you to deem it safe. You might say that a minimum of 3 meters is what you want to achieve, and so you would tweak the algorithm of the AEB activation to activate earlier in the vehicle. So, as the title of the webinar suggests, there is a real blending of industries when talking about autonomous vehicle and the survey industry. One of the key ways that that occurs is effectively any survey application that is taking place today, be it asset management or road survey or any kind of business information modeling, building information modeling, where a UAV or a road vehicle is being used to survey the area. In time, it makes sense that these UAVs and road vehicles will become autonomous in order to be able to do more data collection and repeatable data collection. You want to be able to maybe fly the same path with your UAV 3 times a week and create a new point cloud every time, and then create the map file that shows you whether anything has changed in the environment. Or you may do it once a month over a 12-month period, say, but you might want to have that absolute reference that says, we know we flew the exact same path and we had the same reference point. So any change in the environment, be it trees or land mass moving, is actually true, and you can trust the fact that your data has an absolute reference rather than there being shift in relative data. So hopefully this flowchart shows how the two worlds collide. In theory, you may use LiDAR, you may use cameras in order to survey an area, and from that data you would create a point cloud. At that point, a point cloud is not necessarily inherently valuable because it is a series of completely mutually exclusive XYZ points that may look to the human eye like a recreation of the real world in 3D space. But until you classify the points within the point cloud, they really don't add any value to any further application that you aim to use that data for. So if you classify, say, the lane markings, or you classify the building perimeters in your point cloud, you can then convert it into an actual valuable map for you to use. And that map may be used as an input into your autonomous navigation solution. So you may then navigate within said map and identify anchors that you've classified at the previous stage. And you say, I can identify either that road sign or the corner of that building, and that will allow you to continuously detect that anchor and navigate around it using the anchors as your replacement for GNSS data at times. So when you integrate the map file that you created as part of your survey, that then would feed the absolute position reference as to where am I. You might not know where you are until you've identified 4 anchors in that map. And then from that point on, you know relatively where you are with respect to the anchors, and you can effectively navigate within that closed area with a very high level of confidence. The next stage of autonomous vehicle navigation, how an inertial navigation system can be used in the development and validation of the autonomous vehicle, is that validation. So very commonly, the autonomous vehicle needs to have effectively what is referred to either as a ground truth or a golden truth that will tell you where was I on my trajectory versus where should I have been? And that comes from the INS. And you can say, well, we were off laterally by 20 centimeters, but it was a fixed offset. Therefore, we know that we've got a calibration issue with some of our sensors. And you can go around and do that test again, exactly the same, but you will be able to see if your changes you've made in your algorithm or your sensor calibration actually had the effect you wanted. So the INS can give you that absolute reference, which will time and time again give you the same results, while your variable may be the algorithm or the sensors on the vehicle and how they're behaving. Once you've then validated that your autonomous vehicle is safe, you may decide to use a more cost-effective inertial navigation system, because you've proved that the other onboard sensors are fit for purpose as robust localization method. So you may find that you use a more expensive INS at this stage, and then you downgrade the INS price and performance because you know that your 5 or 6 or 7 other localization methods can pick up the slack and still mean that you have an autonomous vehicle that is safe and valid for the application it's trying to do. So just touching briefly on then how in inertial navigation is used for mapping applications, which can feed that first stage of the autonomous vehicle operation. But going again back to any of these applications that are taking place, both in survey or just in general life, anywhere there is a vehicle being operated that you want repeatable and accurate reproduction of the same trajectory every time, whether that is autonomous taxis or whether it is pipeline inspection or something where you know exactly what it is you're trying to fly over and you want to be able to do that the same every time. Creating your map is a really good way of effectively validating that. So your autonomous vehicle may be flying the route for you that is then collecting your survey data that allows you to win business and win more contracts and provide that valuable map data to a third party. But just to touch on georeferencing, similarly to how I touched on what is inertial navigation, georeferencing is effectively the similar to timestamping metadata into a file. We are effectively applying the latitude, longitude, and altitude and heading, pitch, and roll data to each LiDAR scan packet that is taken, because at any moment in time, an INS knows exactly where it is, and it knows absolutely nothing about the world around it. It's not like a sat nav that has a map file within it, and you're snapping to the road on the heads-up display that you've got on your dashboard. It has only intrinsic data around its position. A LiDAR is the complete opposite of that. It knows exactly what it can sense around it, but it has no notion of motion, effectively. And so the heading, pitch, and roll data that comes from an INS is really critical to being able to rotate that LiDAR data back to the Earth frame and getting you a point cloud that looks like the real world. So in that respect then, this is an instantaneous scan that a LiDAR might be taking, which a lot of you will be very familiar with. And the data on the right is just a trajectory plot that an INS has collected as we drove around from our office to test area on an airfield near our office. And the LiDAR data then, if this is one packet, that would be taken several hundreds, thousands of times every second. If there's, say, for example, with a Velodyne LiDAR, there's 600,000 points per second. You are getting a larger, very, very large amount of LiDAR data to a very, very little, relatively, amount of navigation data. But without that small amount of navigation data, you cannot end up with this kind of data unless you're using another technique like SLAM algorithms. But what this gives you then is every point in this point cloud that is generated is effectively georeferenced with an absolute reference to the Earth frame. So these will all be in XYZ in coordinates in meters, but the origin of your point cloud will have a latitude, longitude, altitude reference to the Earth's coordinate system. So you could tell where is the chimney of that building or where is the corner of that wall in global coordinates. And then that can allow you to make intelligent decisions as to what you need to do, whether it's relative measurements between objects or whether it's things like we're planning a new road, how much mass do we need to remove from the area in order to create the space for the road. And so that could allow you to decide how many vehicles you were going to bring in, how much workforce, what type of vehicles you needed, everything like that. So just very quickly, just some example data that proves how an inertial navigation system can be used on a UAV. So this data was collected by one of our customers in Romania, who flew a bridge, past a bridge, as you can see, and they collected this data using a VLP-16 LiDAR. So they used their own drone, and it had a pre-programmed flight path that was programmed, so effectively autonomously navigating. And you can see the effects of it. This data was collected with multiple passes up and down the bridge and from different locations laterally to the left and to the right of the bridge. The key reason the INS is really valuable is that even though you're flying past the bridge and the other objects multiple times with different approaches and different points of view, the accuracy of the INS data means that you can actually rotate and displace the LiDAR data back to the Earth frame so that all of the points overlay on each other really accurately and you don't get any double vision between the points. And that's probably best articulated from the clarity of the power lines that can be seen in the images, but also the fences around the bridge and the details on the bridge. So without the INS, you either need to do multi-pass processing with something like SLAM, where you're maybe limited on vehicle speed or have a requirement to close the loop in terms of driving back to the location you started, and that maybe mitigates what you can use it for. Say, for example, with a pipeline inspection, where you're operating along a very long baseline, an INS has no need to return to the starting point in order for that data to be georeferenced. Whereas as you fly further along a pipeline, if you're trying to use something like SLAM, which is very good at stitching data together in sequential packets, it may struggle if you've never returned to your starting point so that it can recalibrate its drift. That's just one survey application that could it could both be manually operated, but also it's a prime candidate for autonomous vehicles to service this kind of application, because you can set a starting point, navigate autonomously through your test area, collect the valuable data, and then autonomously return to your landing pad. And that in essence can improve profitability, it can improve efficiency of your operations, and it can improve safety as well if this is in an environment where it's not safe for human operators to function. So just one final point in terms of technical consideration when building and developing autonomous vehicles, there is a significant effect that poorly calibrated sensors on the vehicle can have on the output. So you can see in the image on the right, these are really basic retroreflective square targets that have been surveyed from the sky by a UAV, and they're actually the same data effectively, but this is when the LiDAR sensor was not calibrated in terms of bore sight calibration with respect to the INS's coordinate system. And so similarly, that can have the same effect if the LiDAR is not calibrated with respect to the vehicle's axes. And so that may mean that where you detect an object, say this is trying to detect the landing pad of the UAV, or it's trying to detect something else that it is attempting to inspect, it can mean that you have a false positive in terms of where that object is detected. So that may mean that you think that an object has moved when it hasn't. So it may mean that you action a job to relocate something that doesn't need relocating, or it may mean that actually you fly into something when actually you thought you were going to miss it by a margin. So correct calibration of those sensors is really important, and the inertial navigation system can really help with that, because it can tell you the heading, pitch and roll. And when you've got a constraint like this, like a retroreflective square target that you know the shape of in real life, if you survey it and it appears in multiple places, or it appears as a rectangle instead of a square in your resulting point cloud, you can calculate what your heading pitch and roll offsets are between the INS and the LiDAR. And you can run that whether it's with LiDAR or camera or radar. You can run tests that use the INS as your golden reference. And then you can say, what did my onboard sensor see? And you can set up tests that will allow you to validate whether those sensors are calibrated well or not. But for safety critical applications, this is really important consideration. And it's something that we, at least with LiDAR, have developed a solution in order to calibrate the sensors with respect to the vehicle. Just another example then, the effect of an unbore-sighted LiDAR with respect to the vehicle. You can see on the left, which is the cross-section of a building that was under construction. This is unbore-sighted data, and this is bore-sighted data. So this is the exact same raw data, but with the heading pitch and roll offset between LiDAR and vehicle intelligently calculated. So you don't get any divergence of accuracy on the data when a system is bore-sighted correctly. So, final point is a new product that OXTS have coming this year. Some of you may have seen or attended our launch webinar at the end of December. But OXTS are launching a new INS, which is the XNAV 650. We should have systems available for demonstration in Q1 this year, so not very long at all. And the performance specifications are 2 centimeter position with both real-time and post-processing capability to achieve that 2 centimeters, 0.05 roll pitch accuracy, and 130 grams weight. And these systems will ship with quad constellation GNSS as standard as well, so that you can take advantage of the best satellite coverage possible. And then for real-time applications, you can have up to 250 hertz output. We also have Geo Referencing software, which is developed entirely by OXTS, and that is now compatible with not just Velodyne LiDAR, but also HESI and AUVSI models. So do get in touch with us if this is of any interest for your autonomous or your survey applications. So that's at the end. You can find out more about all of our products on the OXTS website. But now we've got some time for questions. And if you want to contact myself or Frank, or just general inquiries, then do send them to any of the emails listed here.
All right, wonderful. Thank you so much, Paris, for that excellent presentation. And like you said, we will now open up the session for live Q&A from the audience. So as a reminder, attendees, you can submit your questions using that Q&A box, which is in the bottom corner of your screen, or if you're viewing the program in full screen mode via the toolbar at the top of the screen. Just type your question and hit submit. So we do have a couple queued up for you already. The first question that we have is, do you have any systems that would work in total GNSS denied environments, such as indoors?
Actually, it's in the past month, we've announced a partnership with a company called POSIX, who do produce an ultra wideband solution that can be used indoor. We're still developing the first implementation of that, but effectively that will lead us to have a product that works indoors, completely void of GNSS satellites, and that is by replacing the GNSS satellites with these ultra wideband beacons that can provide us an XYZ position update. So if you inquire with OXTS, we can certainly have the discussion around when that will be available, but we are partnering with POSIX to achieve that. So it's a collaboration effort, and we will put you in touch with POSIX and solve the inertial side. It will still be a single box product from OXTS, and you would use an antenna that can detect the ultra wideband that replaces the GNSS antenna plugging into our system.
All right, perfect. Thank you. The next question that came in was asking about some security pieces. How can you ensure the location of a vehicle against a natural or some intentional jamming, like spoofing or the like?
One of the key ways that can be achieved is the addition of the inertial data. So, for example, with natural jamming, whether it's multipath interference or poor satellite coverage, you may find that you get very spurious data coming from GNSS, whether it's intentional or not. And that can be overcome by validating your position and your trajectory against the inertial data. So, for example, like I said, if you saw your position randomly jump 10 meters or 100 meters or 1,000 meters off to the side of where your vehicle currently was on the path of, the inertial data would never see that interference because it would not see a lateral or longitudinal acceleration in that direction. And so with the tightly coupled system in the navigation engine, it would effectively rule out that spurious GNSS update as being completely unexpected, and it would reject it until it was coming in with a level of repeatability that matches that of the IMU trajectory. And so you're naturally very resilient against jamming. Obviously, if it's sustained jamming that is intentional and you're getting data that is putting you in another continent or off on Mars, which certainly can happen if timing issues occur or coverage is very interfered with, that effectively means that you need a system that is not GNSS dependent. And that's what a lot of, at least autonomous road vehicles, trying to do, is not rely on GPS, but exploit it when it is there. So the idea that you have so many localization methods that you don't need GNSS, but if it's there, then why wouldn't you use absolute position updates that are centimeter accurate? Because there isn't really another device or another system out there that can give you such brilliant absolute position updates. Hopefully that answers the question, but if not, then by all means do email us and I'll try and answer it more.
All right, perfect. Thank you. Next in is, for the UAV, how do you apply the concept of detect, see, and avoid?
Intrinsically with the INS, it would have to be paired with both another sensor, another vision sensor like LiDAR or camera, and then an algorithm that has that avoidance, take action capability baked into it. The INS would basically only be able to tell you where you are, and like I said before, it doesn't have any concept of what is detecting other things around it unless you already knew about it and you had it in a map file, or you have another INS on your local network that it knows about. So the concept of detect, see, and avoid is effectively that combination of sensor fusion, both on a hardware and firmware level, effectively, where you can say, I know I am here, I know my LiDAR or camera can see an object at whatever range and at whatever azimuth or your angle. And you can say, I need to take these steps in order to safely avoid the obstruction. And so you can plot that kind of spline that is a safe path through to avoiding the obstruction without either damaging the components on the vehicle or potentially harming any human passengers or animal passengers on board the autonomous vehicle.
All right, thank you. The next question that we have from the audience is, can your solutions with INS operate with the same absolute accuracy in offshore environments, provided that a bore site calibration is carried out over land?
The bore site calibration will give you effectively permanently accurate offsets between the vehicle and the LiDAR or whichever sensor that you have bore site calibrated. The key thing will be the real-time corrections that you're using. So RTK corrections that are used by GNSS currently use local base stations that are on the ground. So if you are in an offshore application, you would be limited using those land-based base stations up to probably around 50 kilometers. And the further you go away, the more absolute error you have in terms of if you're 50 kilometers away, you would not be as accurate as if you were 5 or 10 kilometers away from the base station. But there are more satellite-based correction services than ever before. So there's There are the free services, which are kind of listed under the SBAS acronym, which is this satellite-based augmentation service. But there are also proprietary services offered by companies like Novotel and Trimble that offer this services, which is the precise point positioning. But they do still rely on land-based base stations. So there is a limitation to how well an INS will work as you go further and further offshore. If you're 300 kilometers offshore, at the moment there are limitations to the accuracy.
All right, understood. Thank you. Then the next question we've got is, would the same system be accurate to track a specific object within the same shape? So for example, a person in a crowd or a car in traffic?
Yes, if you had an inertial navigation system on that object or pedestrian or vehicle. So you would be able to, in a sea of people, if your pedestrian that you're interested in was carrying an INS in a backpack, say, you would be able to use your vehicle under test INS to basically say, what is my distance and angle to that pedestrian. Similarly, a vehicle in traffic, because you would have an INS in both vehicles, you wouldn't be concerned with the line of sight between the two. If you were trying to say, where is the vehicle 4 cars ahead of me in traffic? But you could, in certain advanced setups, in terms of advanced tests that are being developed nowadays by autonomous vehicle teams, you may have actually 6 vehicles in your test, and 4 of them may just be cars that are intended to get in the way of the 2 vehicles that are under test, so that you can test how well the onboard sensors of the autonomous vehicle is working in order to detect what's around it and actually detect another vehicle. It might be that there are 2 autonomous vehicles and 4 manually driven vehicles, but you would put an INS in each one in order to be able to track when they moved out the way and then have the data to back that up. So it's similar to how if you have a video as proof on your dash cam when you're in a crash, you can kind of say fundamentally this is what happened if you had the field of view of it. But if something drove in between you and the event, then you would not be able to prove that the event happened or not. If you had an INS in the vehicle that crashed and an INS in the vehicle watching, you might be able to say the relative distance between the two came rapidly to a collision, and then you'd have the data to back it up. So that's why automotive companies are exploiting the inertial navigation data so much in their development.
All right, great, thank you. Next up is, could you mention the accuracy that would be achievable for a given position?
We quote our systems based on a combination of the GNSS receiver's specification and how it performs when in combination with the IMU and the navigation engine. So say for our flagship INS is the RT3000 and Survey Plus products, we quote 1 centimeter position accuracy. And in terms of when that is achieved, that is obviously dependent on good GNSS coverage. And with quad constellation capabilities, that can be achieved more than ever now, even in some urban environments where high-rise buildings are coming into play. So position accuracy in good conditions are, like I say, 1 centimeter, and that would be about 1.5 centimeters vertically because of the spread of satellites. There are not satellites above and below you. They can only be above or to the side of you. And so there is a measurement called dilution of precision, which is better horizontally than it is vertically. And then in terms of position accuracy, when the conditions aren't perfect, that really depends on how bad the conditions are, because sometimes bad GNSS data is worse than no GNSS data because it tries to use some of the data that is there. The IMU then picks up the slack and will try and remove any of the spurious data. But if you went in a tunnel, say, then you can refer to, we publish drift specifications just like any INS manufacturer does, to say after 10, 30 and 60 seconds how far the position will have drifted away from the true location. And the way that we validate that is by driving in open sky conditions and then artificially removing the GNSS data as if the GNSS constellation fell out of view. And we validate that for 60 seconds and then say where was the position versus where we actually were, because we know we can process the data set without any restrictions at all and get that ground truth or golden truth that I referred to earlier.
Right, wonderful, and we appreciate the detailed answers. Unfortunately, that has pushed us right up on time. I was hoping to get one more in. If you submitted a question and it was not answered, know that they will be provided to our speakers, or you can reach out using these contact emails located here. So unfortunately, we are out of time, but on behalf of AUVSI, I'd like to thank you, Paris, for that excellent presentation, and Frank for joining us today for this discussion. So what a great way to start off our year. Attendees, you will receive a link to access this recording, as well as a copy of the slide deck within the next few days. We would once again like to thank our sponsors, Navtech GPS and OXTS, for their generous support of today's webinar. And we are excited here at AUVSI to be kicking off the 2021 calendar year with a full schedule. We hope you'll join us, and to see what's coming up and to register for any of our upcoming events, please just visit our website at auvsi.org, select events, and then webinars. If you have any additional questions or comments, please feel free to reach out to our team at education@auvsi.org. And lastly, today's program is copyrighted by AUVSI with all rights reserved. So thank you all for joining us today, and I hope you have a great rest of your day.